G'day, Chris here and welcome back to ClickSpring. When we set out to make a component that requires the removal of metal, one of the first steps is likely to be deciding what cutting tools we're going to need to make the various features of the part. Some we'll simply have on hand. Others we might need to order in or make to execute a given cut. And if possible, we're likely to make the design conform to all of the other tools that we already have on hand, just to make life a little more straightforward. This next section of the mechanism gives an opportunity to have a closer look at how that same process might have unfolded in the ancient workshop. It's also a good excuse to see what more this part of the mechanism can tell us about the cutting tool technology of the day. We're fortunate that a decent amount of the moon phase assembly survives in the wreckage of the Antikythera mechanism, and so we have decent information regarding its construction. Its function has been well understood since Michael Wright published his model and research in the early 2000s, and Carmen and Decoccio published their analysis in 2016. I'll be covering the construction and function of all of these bits and pieces in future videos. But for now, let's have a closer look at a few of the cut features, starting with the circular plate. Even after 2,000 years, there are some beautifully crisp corners and edges in these openings. The slot and the drive square at the rear of the main opening are both a little less than 3mm wide. The longer slot just above in this image, and a little obscured in the scan from some of the other components, is not much wider than that, and like the rectangular section below it, is defined by crisp straight edges. There's also a fairly neat circular opening for what is assumed to have been for a small ball showing the phase of the moon. Aside from the plate, there are also neatly cut slots found in several of the assembly components too. There's a 0.8mm slot at the back of the contrate wheel. And there's also a small driving square on that same wheel that measures around 2mm across the flats. These are delicate cuts even by today's standards, and they imply a controllable, precise cutting tool, on a scale comparable to modern needle files. Much like early lathe technology, we have clear reference in the literature to Iron Age cutting tools, as well as a small number of surviving items. To date, most examples are fairly coarse and quite large, not obviously suited to the cuts that we've been looking at in the wreckage. So what might the tools used to make this part of the mechanism have looked like? And how could they have been made using the known materials and technology of the day? In a previous video, I described a straightforward process for making files suitable to construct the mechanism. Those files have performed well so far, so I'm inclined to think that the cutting tools for this section were technically similar. It's possible that the smaller squares may have been formed with a punch or possibly swaged, and I'll cover this in a future video. But for this video, I'd like to focus on reamers, saws, and most importantly, files. Because a helpful property of the Iron Age file is that any typical cutting profile can be easily shaped by hand, heat treated, and then put to work within a very short period of time, making it an entirely practical tool-making process for the ancient maker. So before we have a look at the details, let's do a quick recap of that process. Firstly, the blanks are lightly forged into general shape. The surface is then prepared to receive the teeth, ideally flat with a uniform surface finish. Now this step can be completed without the need of a file to begin with. Abrasive stones are good enough to get things started. That would give a surface that after tooth cutting results in a slightly cruder file to begin with. But the surface doesn't need to be perfect to still give an effective cutting tool. That file can then be used to better precondition subsequent blanks, resulting in increasingly better quality files with each iteration through the process. So, much like the lathe, early file technology also has the property that it can be used upon itself to achieve a more capable state. And just quickly before we move on, those chips coming off the blank explain well the long history of the file as a cutting tool. An abrasive stone, for example, will remove material as a fine powder and at a relatively slow rate for the effort put in. But a file, even the handmade variety like these, slices the metal off in long tight curls, removing material much faster and with greater control over the resulting shape. It's a tool that permits complete expression of a maker's vision for a given part. For many thousands of years, and for those cuts to which it was suited, this must surely have been the great appeal of the file over the alternatives. The file cutting is fairly straightforward. The teeth are cut using a sharp chisel that raises a small sharp burr or tooth with each hit. The way the cutting chisel works is that these teeth are formed pointed away from the tang, and so this gives a tooth pattern on the file that will naturally cut on the push stroke. The unhardened file is then further reduced to whatever final profile is desired, again using files and abrasive stones. Once to size, the file is heat treated to make it hard enough to cut. The key part of this heat treatment is the carburisation of the iron, using a process that I've shown in previous videos. It's essentially case hardening of an otherwise non-quench hardenable low carbon iron, using a combination of animal-based charcoal, in this case from strips of leather, and plain salt, combined with a binder of flour and water. This paste mixture is then packed around the file, and then the whole thing is enclosed in clay. When held at a red heat for a short period of time, the carbon from the charcoal diffuses into the metal. This enables the metal to be quench hardened, much like a modern high carbon steel. Once tempered, the result is a durable cutting tool, hard enough to easily cut annealed iron and the low tin bronze of the Antikythera mechanism. It has the sharp bite of a new file, and this size and shape is great for all-purpose cutting. This particular file is roughly equivalent to a modern No. 2 cut, so it removes material at a decent rate for the work put in. If I back off on the pressure a little, it can give a reasonable surface finish too. Importantly, it's clearly a cutting tool, removing material as small chips rather than simply abrading, giving tremendous authority over the material to whoever is driving the file. Now this shape of file is fairly straightforward to make down to a smaller scale, using the exact same process that I've just gone through. Along with abrasive stones, these general purpose files then become helpful for the next step of forming even smaller files. The reason for this is that it tends to be better to start with a slightly larger blank prior to cutting the teeth on very small files. There's a general need to tidy up the edges of a file anyway, by bringing in the edge a little after tooth cutting, so the extra material gives something to cut back from. But more importantly for these small files, extra material helps to resist the tendency for the metal to distort under the cutting force of the chisel. Once the teeth have been formed, it can be taken down to final size using the general files made previously. The need to take care to not distort the blank increases as the files become smaller and more fragile, like for example the file required to form the slot in the contrade wheel. In this case, the final cutting width of the file is required to be less than 0.8mm, so the blank starts out much deeper than the final tool requires to begin with, and then it's pulled back with files once the teeth have been cut. It's worth pointing out that at this scale there's not much to distinguish a file from a saw blade, which is why I find this one interesting. Because we don't have much in the way of direct evidence of small-scale metalworking saws from the period, so I'd like to see if this cutting tool will fit the role. For a standard file, the tang is closest to me when cutting the teeth, so that the teeth cut on the push stroke, the normal situation for a file. But if I reverse the blank and cut the teeth with the tang pointing the other way, I end up with a tool that will cut on the pull stroke or downstroke when held vertically. In this case, my intention is to make a keyhole type of saw blade to use vertically to test out the piercing of plate stock. I've tapered the back edge to give the blade a little bit of room to turn within the kerf, and left it only as deep as required to be just strong enough for practical use. I've also made an extra blade with finer tooth pitch to try that out too. Now the circular part of the opening could of course have been made with a round file, so we'll need a couple of those to test out. This is an interesting shape of file to cut, with the teeth being raised along the length of the blank. Each following line of cuts meshes with those adjacent, so that the entire surface ends up toothed and forming an interlocked spiral pattern. While we're here, here's a quick look under the microscope to compare a modern machine cut file to the hand cut version just completed. Now I've cut this file fairly coarse so that you can see the tooth cutting clearly, but I've also made a finer cut version to test, as well as a coarse and fine of a narrower size to open up a starting drill hole. And finally, we have physical evidence of tapered multi-sided reamers close to the period of the mechanism's construction, in this case specifically noted as octagonal. So let's have a look at one of those too. The process is similar to the other cutting tools. The basic profile is first forged to shape to give the octagonal profile and minimise the amount of filing required in the next step. The 8 surfaces are then draw filed to bring up the cutting edges, followed by heat treatment and then sharpening with an abrasive stone. On a much smaller scale, and more commonly in a 5-sided form, this cutting tool is what a clock or watchmaker would call a broach. Many components in horology are hand-fitted by carefully opening up holes to get a particular fit with other parts. There are numerous holes throughout the wreckage of the Antikythera mechanism, where the principle is essentially the same. To use a brooch-style reamer, first a hole is opened, slightly undersized, and usually by drilling, Then it's opened a little more by gently twisting the broach in the opening, taking off small shavings of metal, and coaxing the hole open to whatever shape and size it needs to be to do a particular job. It might be a tight fit for a fastening pin, or a free running fit for something like an arbor pivot. They can of course also be used to simply clear out material and leave a hole. It'll be interesting to see how this one performs. So after all of that preparation, here's our set of cutting tool options to try out. I'll test the contrate wheel cuts in a future video, but for now let's see how they go working on the circular plate. The wreckage scans show that it was a cleanly cut disc. One way that it may have been formed is by using a cutting tool that I've covered in a previous video, the Scorper and Trammel. The tool makes well-formed chips and generates a bright, accurate cut, suitable for the many disc-shaped components found within the mechanism. The depth of cut is set by tapping the cutting tool lower with each pass on the way to full depth. Once there, a few short strokes separates the part from the parent stock. Then a punch marks the centre and at the same time removes the disc from the shellac that was fixing it to the board. The plate can be cleaned up with stones and abrasive. In this case, powdered pumice leaves a bright equivalent to a modern 800 grit finish. Now of course there are multiple ways to tackle any given job, but I'm going to start with the circular part of the opening to get things moving. The rim of the top plate is close to the outer diameter of this hole, so it's possible the maker just entered the cut from the side with files or a saw, and then simply closed that opening with a perimeter band later. That would have been a good approach, but there's not enough material in the wreckage to be sure either way. So I'm going to start from a drilled hole just to show that either approach would have worked equally well. First up are the round files. The narrowest of the set will work well to get the hole started. Now I could certainly just keep going from here with a larger fine file. The hole is now large enough to receive it to continue the cut. But while I still have some excess metal to work with, let's try out the reamer. The larger reamers like this tend to work a little more pleasantly if the workpiece can be held in hand while cutting. It seems that the feedback on how the tool is performing is a little more immediate, which is helpful for detecting when the cutter is starting to grab or otherwise go astray. Now this matters because reamers tend to be a fairly aggressive cutting tool. After only a few turns and taking things quite gently, you can see that it's really peeling off the metal. Perhaps even more so than a file, it's very clearly a cutting tool, taking off well-formed chips of metal, and so it can be used with tremendous effect. In fact, it's very easy to overdo things with a broach-style reamer like this. Often it only needs a few turns and the cut is done. It leaves a presentable surface finish and a well-proportioned opening. If I was happy to take this hole to full size right now, then this cutting tool would be hard to beat. But of course, it's rarely that simple when making complex parts. As often as not, we need to have the ability to make fine adjustments later on in the process, to accommodate other aspects of a design, or simply to deal with unexpected variations in the sizes of other mating parts. I'll show a little later in the video how once the rest of this plate has been opened up, the perimeter of this hole will be broken, and so the reamer is possibly not the best choice for those adjustments. For complete control over the opening of an aperture like this, the file would likely still have been required. And I've kept the cut well short of the line for now to leave some material on to show you what I mean. The next cutting tools to test are the saw blades, first using the finer cut of the two. As for all of these tools, I've gone for the minimum viable tool to prove the point, but it's easy to imagine a simple supporting frame to accommodate a piercing blade like this. Having said that, the complete freedom of movement of a keyhole saw, being able to send it in any direction without having to accommodate any frame, is helpful too. I found that just a light finger pressure on the blade was enough to stabilise the blade during the stroke, and it also gave great control over the depth of cut. I've completed this last section with the coarser blade, and it just ripped through the material. I couldn't ask for better performance from a modern saw blade. Again, I've left the cut well short of the line to give plenty of material to test out the rest of the files. This is all still just a hair short of the line, so that I can walk it all in once I know the dimensions of the other parts. But the main thing to take away at the moment is that the corners and lines are comparable to what we could see in the CT scans of the wreckage of the mechanism. Okay, next up is this little notch and the hole for the driving square. There's not really that much to the notch, it's just a light plunge cut. The side of the cut closest to the centre of the plate ends up having a slight angle when complete, but I'll leave that where it is for the moment until I've made the other components. You'll have noticed in the scans that the hole for the driving square is set at an angle to the opening, something like 20 degrees. Now it's not obvious that this wasn't simply an arbitrary thing, but I'll put in the opening at the same offset angle and maybe we can see if the orientation means something later on. Again, I've left a small excess of material on to get a snug fit with the driving square when I make it in a later video. Now before I continue with opening up this circular section, here's a bit more detail on that issue I mentioned previously, about using a reamer once a whole perimeter has been broken. I've made a test piece to simulate the current situation of the workpiece. You can see that now that the side of the hole is open, the reamer has somewhere to catch on its way around the cut. This creates a tendency for the reamer to not track correctly, and you can even hear that it's now a much less pleasant interrupted cut. There's a real possibility that it might catch on an edge and dig in and ruin the part. Of course, I'm simulating the need for this video, and with care it can be made to work, but at great risk to the part. If this sort of late stage adjustment was genuinely required, this would probably not be the best choice of tool. So my general impression from all of this testing is that although the various alternative cutting tool options would have been useful in certain situations, they most likely occupied a supporting role, with files of various shapes, sizes and cuts likely occupying the main role as the cutting tool of choice for most operations. The origins of the Iron Age file are now mostly obscured. It would be more than 1500 years from the construction of the Antikythera mechanism until the Da Vinci sketches of a machine-based file cutting process, and longer still before the construction of a reliable file cutting machine. For the vast majority of human history, this primary cutting tool has been made by hand. The Antikythera mechanism is evidence of the finely engineered work possible with that and similar early handmade tools. So as much as the machine's story is of mathematics and astronomy, it also carries part of the origin story of early artisanal toolmaking, where knowledge and common raw materials were combined to make the exact cutting tool required for the task. Thanks for watching. I'll see you later.